Assalamualaikum and hi. We are from Group 5. Today we will gonna present about structural analysis of a real frame building system for course BFC 20903 Mechanic of Material. For our group members, we have Nur Fitriana binti Ahmad, Suryatul Zulainur binti Zulkifli, Muhammad Faris Aiman bin Adi Shamsul, and myself, Muhammad Isaac Daniel bin Abdul Malik, and lastly, Shakir Haikal bin Sazali. The main objective of this project is to perform a structural analysis of an elevated water tank system. The analysis includes load calculation, determination of shear force and bending moments, stress evaluation, buckling analysis, and torsional analysis. Through this calculation, we can assess the structural safety and stability of the selected frame system.
Our selected structure is located at University Tun Hussein of Malaysia, UTHM Parit Raja Johor, specifically in front of the Faculty of Technical and Vocational Education FPTV. This location was chosen because it provides easy access for site observation and data collection. In addition, the structural members such as columns and beams are clearly visible, allowing accurate measurements and analysis to be carried out. The selected structure is an elevated water tank, which provides a practical case study for applying mechanic of material concepts such as load, transfer, stress, analysis, buckling, and torsion.
Now I will explain about the load calculation for the slab. Before that, my name is Muhammad Faris Aiman bin Adi Shamsul. My meter number is CF250235. Okay, first, the slab thickness is 0.2 meter and the density of concrete is 25 kilonewton per cubic meter. Therefore, the slab weight of the slab is calculated by multiplying the concrete density by the slab thickness. So, 25 multiplied by 0.2 gives us 5.0 kilonewton per square meter. Next, we add the floor finish load, which is 0.594 kilonewton per square meter, and the plaster load, which is 0.216 kilonewton per square meter. After adding this load together, we obtain the total area load of 5.81 kilonewton per square meter. Finally, the area load is multiplied by the tributary weight to determine the load transfer from the slab to the beam. The final load transfer to the beam is 11.62 kilonewton per meter. Next is the beam design load calculation. First, we will calculate the self weight of the beam. The beam dimensions are 0.3 meter by 0.6 meter, and the concrete density is 25 kilonewton per cubic meter. Using the formula, the beam self weight is 25 times 0.3 times 0.6, which equal 4.5 kilonewton per meter. Next, we add the beam self weight to the load transfer from the slab. So, the dead load GK is 11.62 plus 4.5, giving a total of 16.12 kilonewton per meter. Finally, the design load is calculated using load combination W equal to 1.35 GK plus 1.5 QK. After substituting the value into the equation, the design load is 27.76 kilonewton per meter. This design load will be used for the structural analysis of the beam.
This slide shows the calculation of the column load. First, the beam reaction was determined using equation R equal to WL over 2, which gave a reaction force of 55.52 kilonewton. The total load transferred to the column from the level 5 was 1110.4 kilonewton. An additional 80 kilonewton load was considered. Therefore, the final column load is 1190.4 kilonewton. This slide presents the distribution of the water tank load. The tank's self-weight is 1402.8 kilonewton, while the total tank load is 15,431.1 kilonewton. This load is distributed among the supporting columns, resulting in a load of 482.22 kN per column. After combining it with the existing column load, the actual column load becomes 1672.62 kN, which was used for the subsequent structural analysis.
Based on the calculation in the diagram shows, the maximum shear force Vmax is 55.452 kN. This value occur at the support at the structure and represent the highest internal forces that make a shear failure within the structural section. Next, the maximum bending moment Mmax is 55.52 kN. This maximum value occurs at the midspan of the structure, which experiences the greatest bending effect due to the uniformly distribution load. From the shear force diagram SFD, the shear force decreases linearly from positive 55.52 kN to negative 55.52 kN as a result of the uniformly distributed load. Meanwhile, the bending moment diagram BMD shows a parabolic shape indicate that the bending moment increase until it reaches the maximum value at the midspan before decrease back to zero at both support. This result indicate that the structure distributed the applied load symmetrically, and midspan is the critical section that require attention in design process because it experienced the highest bending moment. Based on the stress analysis conducted on the structure, three types of stress were evaluated. First, bending stress, second, shear stress, and axial stress. The result shows that the bending stress is 3.084 megapascal, indicating the stress developed due to the bending action of the member. The shear stress obtained is 0.31 megapascal, which represents the stress caused by the shear force acting on the structure. In addition, axial stress is 10.45 megapascal, resulting the axial load applied along the member. This value provides an indication of the structure response under the given load condition and important for the assessing the structural performance.
For buckling analysis, the slide presents the buckling analysis of the selected column. Buckling is a failure mode that occurs when a column subjected to compression becomes unstable and bends sideways before the material reaches its strength limit. To evaluate the column stability, Euler's buckling formula was used. Based on the calculation, the critical buckling load or PCR is 5,257 kN. The actual load acting on the column is 1,672.62 kN. Since the critical buckling load is much greater than the actual load, the column is considered safe against buckling. Therefore, the selected column size and support condition are adequate to resist the applied compressive load.
Now, this slide presents the buckling assessment of the reinforced concrete column. The parameters used in the analysis include a column height of 20 meters, a K factor of 0.5, modulus of elasticity 25 GPa, and a moment of inertia 0.00213 meter to the power of 4. Using Euler's buckling equation, the critical buckling load PCR was calculated as 5,257 kN. When comparing this value with the actual load acting on the column, the critical buckling load is significantly higher. This indicates that the column has sufficient capacity under the applied. Therefore, it can be concluded that the column is structurally stable and safe against buckling failure.
Next, I will explain the torsional analysis of the beam. Torsional analysis is carried out to determine whether the beam can safely resist twisting effect caused by the applied load. From our calculation, the torsional moment T is 55.52 kN meter. Using this value, we calculate the torsional shear stress, which is 0.77 megapascal. This value indicates the amount of shear stress produced due to twisting action on the beam. Next, the secondary moment MS is 66.9 kN meter. This moment is considered together with the bending moment to ensure the beam has sufficient strength under combined loading condition. Based on this result, the beam is able to resist the applied torsional effect and remains within the allowable design limits. In addition, the columns have a buckling capacity that is much higher than the actual applied load, which means the columns are structurally safe against buckling failure.
This slide presents the secondary load analysis. Secondary load occurs when the column experiences a small deflection due to the applied compressive load, creating an additional bending moment known as the delta P effect. Based on the column height of 20 meters, the assumed deflection is 0.04 meters. Using the actual column load of 1,672.2 kilonewton, the calculated secondary moment is 66.9 kilonewton meter. This indicates that the secondary load effect is relatively small and does not significantly affect the structural performance.
In conclusion, based on the analysis that has been conducted, the water tank structure study was found to be able to safely accommodate all the applied load. The stress value obtained were still within the allowable limit, while the column was also found to be stable and not at risk of buckling failure. In addition, the effect of torsion and secondary loads did not have a significant impact on the performance of the structure. Therefore, this structure can be considered safe and stable under the load conditions analysis.